Hello, welcome back to my channel. This is the second video from the new series which is dedicated to my new project, which is a 6v6 based tube hi-fi amplifier. The project is taking shape in my head and on paper, so I would like to tell you a little bit more than I did in the first video. I would like to go a little more in deep with the design. Thank you very much for your attention. I hope you enjoy this new video. This is a quick view of how the amplifier will look like. As you might see, I made a little bit of changes to the initial design. The major one is the decision to develop a two chassis amplifier. The power supply will be built on the basis of a separate chassis. So in this moment you are just seeing the amplifier. Of course you are not seeing the power transformer and also you are not seeing the filtering impedance for the high voltage. So this amplifier will receive all the voltages, the high voltage for the tubes, also the low voltage for the control sections, the low voltage alternate current for the heaters, will receive all those from a separate chassis. So these are the four power tubes, 6v6 GT by Fivre, for an output power, according to my recent simulation, around 15 to 16 watts. These are the two output transformer. The impedance of the primary of the output transformer is 8000 ohm. These are the two phase splitter tubes feeding the four power tubes. They are two ECC81 tubes. You might remember I initially decided to build a phase splitter on the basis of octal tubes, but then I decided to go to smaller novel tubes. These are two EF86 tubes, which are the first gain stage within the power amplifiers. So this is the left channel power amplifier, this is the right channel power amplifier. The first stage will be an EF86, which I really like for the sound. The two power amplifiers, left and right channel, will be completed by two Magic Eye tubes. You see here, these are Russian EM80 tubes, which will show the instantaneous output power through a green glow on the screen of the Magic Eye tubes. These are the tubes which will be deployed for the preamplifier. Again, you might see some little bit of difference since last design. These are two 12AU7, so ECC82, which will be the core part of the preamplifier. And these are two ECC83 tubes, so 12AX7, which will be part of the phono preamplifier. I plan to deploy AC heaters for all the tubes, with the only exception of the two tubes which will be deployed for the phono preamplifier. For those two tubes only, I plan to deploy DC heaters. Here you can see a draft view of how the power supply section for my new tube amplifier will look like. As I mentioned before, this will be a separate chassis. Of course, now you're not seeing the cabinet, but just to give you an idea. As you can see, I plan to deploy a tube rectifier, so a 5U4 tube for the rectification of the high voltage. Then we have the 10 Henry smoothing impedance for the high voltage. Finally, we have the power transformer feeding all the different necessary voltages to the circuit. You see it in upside down position, but of course it will be mounted in the correct position when the chassis will be finalized. This is the power amplifier schematics, a part of that, at the current stage of completion. We have on the right the output transformer, then going from the right to the left we have the two power tubes, two 6v6 GT tubes. Then on the left again we have the phase splitter tube, which utilizes two sections within the same tube. We can see some highlights for the power amplifier. This will be a fixed bias amplifier, so I will design a separate power supply stage which will feed the polarization voltage to the two tubes. You can see bias A and bias B in this picture. Also, the two tubes will be configured as a penthod. You can see the global arrangement here, and the screen will have a separate power supply tap for penthod operation. Let's imagine we have a signal at the input of my phase splitter. You can see here. At the two outputs of the same stage of the phase splitter, we have the two copies of the exact input signal, of course a little bit amplified, and the two copies are one at the opposite phase of the other, so they are 180 degrees apart. Those two signals are then fed to the input of the two power tubes, of the two 6v6 power tubes. Then, if the amplifier is polarized as class AB1, this means that each one of the two power tubes takes care of a portion of the signal, as you can see here. So each 6v6 amplifies little more than a half of the incoming signal. As you can appreciate, class AB1 is a sort of middle between class A, where each tube takes care of the whole signal, and class B, where each tube takes care exactly of 50% of the signal. It's the output transformer which sort of combines the two signals, the two contributions, and produces the output signal, which in this case is this very nice sine wave. Here you see part of the power supply unit. As I mentioned before, the power supply will have its own separate chassis from the main power amplifier cabinet. So the two units, power supply and power amplifier, will have two different chassis. They will be connected together through a cable. So here you see part of the power supply schematics, the one feeding the high voltage you see on the main part of the picture, another part feeding the heaters, the AC voltage, AC 6.3 volt for the heaters, you see on the top part of the picture. The output high voltage taps from the power transformer go at the input of the tube rectifier. Here I have chosen a 5U4 GB tube, which is capable to deliver 275 milliampere. You might remember my initial idea was to deploy 5Z3 tubes, which are wonderful aesthetically. I have plenty of those. They are very good tubes, very good vintage tubes, but I was afraid about their capacity to deliver the necessary current to the circuit. The 5Z3 tubes, in fact, are capable to deliver 225 milliampere. And again, I was worried that this would not be sufficient. On the contrary, the 5U4GB tube are capable to deliver 275 mA, so this gives a little bit more margin for the amplifier. Then we have the smoothing impedance, 10 Henry, and then we have the different high voltage steps, voltage being defined by the value of the resistors you see there. Let's now see step by step how a push-pull tube amplifier is designed. The starting point is the datasheet of the power tubes. In this case, you can see a datasheet of the 6V6 GT power tubes. As one of the most important information we can find in the datasheet, we have the plate characteristics, which is a graph, as you can see here, which has in the horizontal axis the plate voltage across the tube, and in the vertical axis the plate current which is flowing through the tube. The relationship between plate voltage and plate current is shown here for several different values of this EC1 you can see here. This EC1, which is sometimes referred as VG, is the voltage between the input grid of the power tube and the cathode of the same power tube. For AB1 polarized amplifiers, this EC1 or VG is always negative, and in fact you can see the different plots, 0 volt, -5, etc. This quantity represents my input signal. You will remember the signal I have the output of the phase splitter. In this case, as you can see, the input signal amplitude can swing from 0 volt to -35 volts. This dotted line is very important. It reports the situations where I have a dissipated power exactly equal to 12 watt, which in this case is the maximum allowable for the 6V6 GT tubes. So when we will decide the operating point, we will see later, we have to pay attention not to go on the right of this dotted line. As final note of this picture, all those plots refer to screen voltage equal to 285 volts. We will see later what happens if the screen voltage is changed from this figure, but for the moment let's assume it's constant and it's equal exactly to 285 volts. Let's first choose a suitable idle operating point. According to the datasheet, the maximum plate voltage is 300 volt. So again, let's stick with that. If we want to stay at about 70% of maximum possible dissipated power by the tube, and if the maximum voltage is 300 volt, then it means that the current for my idle operating point is 28 milliamps. So let's plot this operating point. As you can see, this sits in between the two EC lines, as you can see, -20 and -25. By looking at the graph, we can guess that the desired operating point involve a polarization voltage of -21.5 volt. This is the idle polarization voltage I need to apply to the power tubes. This is again the voltage between the input grid and the cathode of each one of the two power tubes. As the amplifier is a fixed bias, maybe we didn't tell before, this means that I will need to design a power supply module which can feed the power tube grids with this voltage. Let's now plot the load line. We have an 8K primary impedance for the output transformer. This means that each one of the two power tubes is seeing a 4000 ohm impedance. So using the Ohm's law, we can define that this line sits between the 400 volt zero current point and the 0 volt 100 milliampere point. We then shift this line till we cross the defined operating point. Please do remember that we are just seeing the simulation for one tube only. As you remember, in push-pull we have two tubes, and we will see later how the two tubes combine together. So for the moment this is our load line, and my input signal swings across this load line around the defined operating point. This is not the only load line we need to draw for an AB1 polarized amplifier. For small signals around the operating point, the amplifier in fact will work in class A, so we will have both tubes conducting and working. As soon as the input signal amplitude gets higher than a certain amount we will see later, the amplifier cannot work in A class anymore, so one of the two tubes stop conducting. So we need to draw another line. We need to draw a line which can report the situation when one tube only conducts over the tubes pair of the push-pull amplifier. So let's draw this new load line. You can see in orange-yellow I would say. This new line sits between the 300 volt 0 amps and 0 volt 150 milliamps points. This is because when one tube only is working, so when we are in class B operation, that tube is seeing only half of the output transformer primary windings. As the impedance ratio is the square of the turns ratio, so we understand that the only working tube is seeing 1/4 of the global plate-to-plate transformer impedance, which in this case is 1/4 of 8 kilo ohm, so 2 kilo ohm. You see where the two load lines cross. This is where one of the two tubes stop conducting and leave all the work to the other tube. This composite load line is very important, and this is where the input signal swings. If the grid goes more negative, so my input signal gets lower in amplitude, the signal follows the line down on the right. On the contrary, if the grid goes more positive, then it follows the load line up to the top left. Through this graph we can calculate the amplifier expected output power. As you know, power is equal to voltage multiplied by current. In order to find the numbers to feed this formula, it's very important to see where the B-class load line, the orange one, crosses the line where EC is equal to 0 volt. EC 0 volt, so VG 0 volt, is where is the situation where I have the maximum input signal. As you remember, AB class, in AB class amplifiers I cannot have grid voltage over 0 volt. For the voltage figure of the formula, I will need to calculate the maximum swing over the tube plates, which in my case is 300 volt, which is the maximum, minus 65 volt, which is the projection of the point we have found before over the horizontal axis. The maximum current in these conditions for the maximum amplitude signal is 118 milliampere. So putting all these numbers into the formula, we get the voltage swing, which again is 300 minus 65 volt, multiplied by the peak current, which in our case is 118 milliampere, divided by 2, because remember we need to find the RMS power value. On the contrary, for the moment I have the peak-to-peak voltage, so I need to divide by 2. And then we get this number, which is more or less 15 watts. The second number we can calculate is the maximum output power in A class. We can calculate this quantity by looking at the crossing point between the two load lines. In this case, the expected output power when both tubes are conducting, so when the amplifier is working in A class, is 2.9 watts. So this amplifier will work in A class till 2.9 watts. Again, the load lines are a very powerful instrument, and through that we can have an idea of the amplification of the power stage. This is not strictly the gain, because you see the load line is not a straight one. Of course, it's a composite load line, so calculating the real gain would imply some more analytical math. But anyway, we can estimate that the amplification of the power stage comes from the division between the delta, the output voltage delta, and the input voltage delta. We know what the output voltage delta difference is. This is the swing of the voltage across the tube's plate. We calculated it before. It's 300 volt minus 65 volt, which is 235 volt. This is our output voltage delta. Again, we know what the input voltage delta is. You remember my operating point sits at minus 21.5 volt. This is the voltage, the other voltage applied to the grid of the tube, which is the input. So this is exactly our input voltage swing, because as you remember, the input, the voltage applied to the grid, cannot go over 0 volt. So my input swing is between 0 volt and minus 21.5 volt. This is just a simplification. You remember that on AB polarized amplifiers, the input voltage can go even lower than minus 21.5, but you know, just to have an idea of the amplification. So by dividing 235 volt by 21.5 volt, we get roughly 10-11 times, which is the amplification factor of my output stage. This is another graph we find in the tube datasheet. This is more or less the same we have seen before, so still we are speaking about load lines. So on the horizontal axis we still have the plate volts, in the vertical axis we still have the plate current. The only difference is that we see many plots. Each plot reports the situation for a different screen voltage. We see screen voltage of 300 volt, the top plot. Then going below we see lower figures for the screen voltage. We can see that the higher the voltage applied to the screens, the higher the plate current, which means, as we have seen before, the higher the output power of my amplifier. Another very important instrument for sake of tube amplifier design is the transfer characteristics, which typically comes with the same datasheet of the tube. Here we are seeing those for the 6v6 tube. We can see that in the horizontal axis I have the grid voltage, which is basically my input signal voltage to the tube. In the vertical axis I have the plate current in milliampere. As you can see, the higher amplitude my input signal, the higher the current through the plates of the power tube. Also, the higher the voltage applied to the screen, again, the higher the current flowing through the tube's plate. As you can see, I have reported my operating point here in the blue line. On the horizontal axis, this point sits at minus 21.5, as you remember. In the vertical axis, you remember the current, the idle current, is 28 milliampere. In order for me to explain the role of those transfer characteristics, let's one moment imagine we don't have an AB class amplifier like the one I am designing, but an A class amplifier. In this case, the operating point will be different, of course, will be on the higher part of the graph, as a single tube will take care of the whole waveform, of the whole input signal. You can see, in fact, the waveform reported in the bottom of the picture. This is my input signal, and the waveform reported on the right part of the picture is my sort of output signal. So this is the this reports the variations of the current through the tube's plate. Let's now come back to our case, which again is an AB polarized class amplifier. As you remember, we have two tubes in our case. Every tube takes care of a portion of the signal. So in this case we have to draw two different graphs, one for the upper tube, another one for the lower tube. The two graphs are horizontally aligned at the operating point. Let's now concentrate on the top graph, which is plotted for one tube. The input signal you see on the left of this picture, this is a sine wave. This represents voltage variations applied to the tube grid. Those variations cause changes on the plate current of the top tube. You can see that the resulting variations of the current plate, you can see those in the mid top part of this picture. So this is the resulting waveform. The top part of this waveform is hopefully perfect without any distortion. On the contrary, you see the bottom part is not complete, first of all, and then we also have distortion. This is because, as you remember, on AB class polarized amplifiers, each one of the tubes take care of a portion of the signal. As you understand, this is the difference between AB class amplifiers, which we are seeing now, and A class and also B class amplifiers. On AB class, as you can see, each tube takes care of in this case, more or less 70% of the waveform. On A-class amplifiers, each tube takes care of 100% of the waveform. On B-class amplifiers, each tube takes care exactly of 50% of the waveform. For B-class amplifiers, the operating point would be in the lower part of the graph. Going to the other graph, which is relevant for the second tube, the bottom graph, you see the behavior is exactly the same but opposite. Again, in this case we get an output waveform which is perfect for the lower part in this case, but not for the higher part. Just as a reminder, the input signal for each one of the two tubes come from the output of the phase splitter. So each tube is fed by the same signal, but the two input signals are one at the opposite phase of the other. So at the output of the two power tubes, we have these two waveforms, which again represent variations of plate current. Those two plate current variations are then combined by the output transformer. At the output of my output transformer, I have the resulting waveform, which in this case, as you see, is a hopefully perfect, which means low distortion, perfect sine wave. So the resulting waveform comes from the combination of the two waveforms we have seen before. So this is the final information for this video. In the next video we will examine the other stages which I'm currently designing, the phase splitter, for example, also the first gain stage for the power amplifier and the preamplifier, and so on. For the moment, let's look again at the final piece of information I would like to give now, which is related to the transconductance. This is another measure of the tube's capacity to amplify. This time we want to see the current variations. So the transconductance is the ratio between the current variations and the voltage variations. Current variations are measured at the plate, I would say at the output of the tube. Voltage variations are measured at the input of the tube. In order to measure this figure, we utilize the transfer characteristics. We can guess that the steeper the transfer characteristics are, the higher the transconductance, because the higher the capacity of the tube to amplify, the capacity of the tube to drive current variations at the plates with the same voltage variations at the input. In our case, if we concentrate just on half of the signal, and we begin by calculating the current variations, we have 70 milliamps minus 28 milliamps. You will remember 28 milliamps is where my operating point is. So this is the current variation driven by the tube. So we have 42 milliamps. If we divide 42 milliamps by 10.7 volt, you will remember the input swing is exactly double this number. Here we are concentrating on just on half of the signal, so we have 10.7 volt. And the result is the one you see reported in this picture. And I'm quite happy because this figure is consistent with what we find in the tube datasheet as well.